Alright, so now we're going to be covering problem number 1145, which is marked as a medium problem on LeetCode, and the problem name is binary tree coloring game. So two players play a turn-based game on a binary tree. We are given the root of this binary tree and the number of nodes n in this tree, n is odd, and each node has a distinct value from 1 to n. Initially, the first player names a value x with x belonging to 1 to n inclusive. So it belongs to 1 to n, so it can be in that range. And then the second player names a value y, again with this same range, and y is not equal to x. The first player colors the node with value x red, and the second player colors the node with value y blue. Then the players take turns, starting with the first player, that is the player who has named the value x. In each turn, the player chooses a node of their color, red if player 1 and blue if player 2, and colors an uncolored neighbor of the chosen node, either the left child, the right child, or the parent of the chosen node. So you see, we have to also traverse up. Okay, so it is a binary problem, but since we need to go up as well, so we somewhere you can see that the intuition says that we have to basically be forming a graph from this, right? An undirected graph, because we do not have access to a parent whenever we are considering a binary tree. It only has access to left and right children. But if we want to access the parent as well, we have to convert it into a graph. Okay, so first thing we noted in that problem, so that is one thing, that we have to convert it into undirected graph. Okay, till this line we have got this information. Now, if and only if a player cannot choose such a node in this way, they must pass their turn. If both players pass their turn, the game ends, and the winner is the player that has colored the more nodes. You are the second player, that is the player who has marked the value y, that is you are marking with blue. Now, if it is possible to choose such a y to ensure you win the game, return true. If it's not possible, then return false. Okay, so that's the condition given to us. And now let us look at this example. So basically x is equal to 3. 2 is not present right now. 2 is the blue node that we have to choose ourselves. Okay, so let us just form the binary tree. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And 3 was already marked as red by x. Now I am me being the second player, I have to choose a node in such a way that I get more blue nodes than the red nodes. So basically, if I choose 2 as the node, in the first iteration, x is always going to start the game. So x basically colors the node, that is its parent 1, as red, its left and right children also as red. So basically 6 and 7 are also marked as red. Now it is our chance. Okay, so we have to choose a node closest to 3 so as to get nodes in the blue color. So now all the nodes falling in this subtree would be colored blue, because now this is red, right, and these are all blue. So now the path of the red coloring has stopped here, and we have basically captured all this area for the blue part. Okay, so it is true, we have to return true if we are able to win the game. Okay, that is what it is asking, right? If it is possible to choose such a y, that is the blue colored node, to ensure that we win the game, and we win the game when we have more colored nodes. So obviously in this you can see that we have 1, 2, 3, 4, 5, 6, 7 nodes, and 7 nodes marked as blue, that will be marked as blue, and only 4 nodes that will be marked as red, since it goes over to this parent, the left child and the right child only, right? So that is the first example. Now going over to the second example, we have root as 1, 2, and 3, and the player 1 has chosen x is equal to 1. So it would basically in the first iteration itself, it would go to 2 and 3 and mark these as the red. So we have no possibility of marking blue anywhere on this, because red has already taken, or the player 1 has already taken the whole tree and captured it by red. So we cannot mark it, and therefore it is false, that we won't be able to win the game, that we won't have blue colored nodes more than red colored nodes. In fact, we won't have any nodes in this, any blue colored nodes in this case, right? So that is the problem. And now let us get to the intuition part. Okay, so this is my solution. Let me show you. So it is very obvious that we're going to be using BFS, since we're going to be traversing the graph, or it is a binary tree, but we are going to be converting it to a graph, right? And we're going to be going over it level by level, right? So to win, the player 2, that is B, that is you, must choose a blue node such that their reachable area, or the subtree falling under the node, is strictly larger than player 1's, that is the red player's area. So we want to block the player 1 who starts from node X from expanding into too many nodes. So there are 3 regions the player 1 can potentially expand to from node X in its first turn itself. That is as we see, the left subtree it can go to, the right subtree, and also its parent, and also the rest of the tree, that is the parent of X and everything connected to this parent. So as player 2, you can choose any one of these 3 regions to start your coloring from, and win if the size of your region is greater than n by 2. Now this n by 2 comes from the fact that since there are n nodes in the tree, if we choose n by 2, basically the size n by 2 greater than n by 2, then we have actually, what we have done is covered those nodes with blue. So those nodes would obviously, since they are greater than n by 2, we win, right? So the condition is met that we have more blue colored nodes than the red ones. So that is the answer. Okay. Now our approach is going to be something like this. So we map the parent nodes using a pre-order traversal first. This helps us move up from any node. Then we use BFS to count how many nodes can be reached in each of the three regions. From the parent of X, let us say it is the number or the count of the nodes that can be reached from the parent of X is A. Then the count of nodes that we can reach from the left child of X is B, and the count of nodes that we can reach from right child of X is C. So try starting from any of these three zones. If any of these three zones contains more than n by 2 nodes, the player 2 can win. As I discussed, it should be just greater than n by 2, because we are considering we just want to having the number of blue nodes greater than red nodes in order to win, right? And since it is something like only a 2 coloring problem, right? So that is why we have n by 2. In case we had a 3 coloring problem, we would have the condition as n by 3. Okay. So try starting from any of these three zones. If any of the three zones contains more than n by 2 nodes, player 2 can win. If none of the three regions surpasses n by 2, then we return false. The same condition. And complexity, basically O of n, each node visited once during pre-processing and once per BFS, and O of n again, space complexity for the parent map, visitor set, and BFS queue. So now the most important part, the coding part. So let us go over it. So we need to pick a blue so that the red can't expand too much. That is, the counter of blue nodes should be greater than counter of red to win. So that is the main crux of the problem. And now let us get to the solution. So we declare root x of tree node star type. That is the node with value x. That is the red node. That is the node which player 1 has marked, right? So that is the red node. Unordered map also we take, which will be storing the node value. Which will be storing the child's value and the parent. So child's value is of int type and the parent is of tree node star type. And now we start our BFS to count the size of subtree or the region starting from the given node, right? So the size of subtree is counted by this BFS. So we declare it of int type because it would be returning a integer value. So int BFS node star root, it is taken. So we first check if the root does not exist, that is if root is null, we return 0 obviously, since it won't have any size, right? And now we are basically starting a standard BFS, that is q tree node star q. We push the root into the queue, and counter is equal to 0. Counter is basically going to tell us the size of the subtree, right, for the current node that we have passed. Okay, and while the queue is not empty, we basically traverse in the queue, and we're going to be going level by level, right? So current is basically q dot front, and we extract the current element of the queue and pop it out from the queue. Then value is basically current's value, and we set the current's value as 0, that is mark the node as visited. Once we actually go over it, we mark the node as visited, and when we basically mark the node as visited, we increase our counter because we have captured that particular node. That is the size of the subtree increases by 1, so counter plus plus. And now we're going to be covering the unvisited neighbors, that is the left child, the right child, and the parent of that particular node. So if current's left exists and the current left's value is not equal to 0, that is it has not yet been marked as 0, that is it has not yet been marked as visited, then we can go over it and push it into the queue. Similarly for the right child, if the current's right exists, that is it is not null, and the current's right's value is not equal to 0, we push the right child of the current node. And similarly now we access the parent node. If the parent, that is map value, if the parent exists and the parent's value is not 0, then we push the parent into the queue. And finally we return counter, that is the size of subtree of the current node. And for building the parent map, we have used the pre-order function to get the parent map and locate the red node. So a standard pre-order function where we first check if the root is not equal to null, and if the root is null, then we return x is basically the red node, right? And if root's value is x, then root x is equal to root, that is if the value of the root is equal to the red node, so we make the red node that value, right? And we basically go over to the left and map the left with the parent, left child with the parent is mapped, and secondly the right child, if it is not null, then we map the right child with the parent again. Okay, and then we call the pre-order function for the left and the right child. So this is basically a recursion function. We have called it to build the parent map and locate the red node. Now once this has been done, we move over, and this is our main function, boolean of binary tree game winning move. It takes a root of tree node star type and n and x, where n is the number of nodes in the binary tree and x is basically the red node that is being marked by the player 1, right? Now step 1 is to pre-process to find the red nodes and the parent links. So we mark the pre-order, we basically get the red node, and the parent we have mapped to the in the unordered map, right, which is known as map itself. So map of root's value is null, that is the root has no parent. So since basically, let me draw it for you. Let us say this is the root and we have a tree below it, right? So for each of these there is a parent that is existing, but for the root there is no parent, so we map the root's value to null. And step 2 is to block the red node where our player 1 would start. So we're doing this, root x value we mark as 0, that is it has been visited, and now we have blocked the red node. Step 3 is count all 3 disjoint zones via BFS. So 3 zones were the parent side, the left subtree and the right subtree. So A we call BFS of on the parent map of x, then BFS on root x is left, basically where we are starting from. A would return for the parent side, then B would return from the BFS side, from the left subtree side, and BFS C is basically from the right subtree side. Now case 1 is pick the parent of x as blue, that is counter of left subtree plus counter of right subtree plus 1 for the current node less than counter parent. So case 1 is this one. Okay, this is what we are basically explaining, that is A plus B plus 1 if this is less than equal to C. Sorry, if this is less than C strictly. So what we have done is we have picked the parent of x as blue. So we had this, right? This is x and this is the parent node. So if the parent node of x we have chosen as blue in our tree, let us say this is the tree that has been given to us, right? If this is the tree, if the parent we choose as blue, if we mark it as blue, then the counter from the left subtree plus the counter from the right subtree plus 1, if that is less than the counter of the parent, right, then we have actually then we can actually confirm that the number of blue nodes would be actually greater than red, right? And similarly for if we pick the left of x as blue, so the right, this is the right one and this is the parent, so the counter of right subtree plus the counter of parent plus 1 for x, if that is less than the number of nodes that are coming from blue, because this has been marked as red, all of this subtree is also marked as red and x is already marked as red. So the remaining trees in the node, we have to check if those subtrees counter, that is if the counter of the blue from the right subtree is actually greater than the added counter of the one coming from the right subtree. This is the left subtree, sorry. So this is the left. So we check if the counter of the, let me redraw it for you for clarity. So let me show you. This is the x node. Let us say, let me just draw it clearly for you. Okay, this is the graph, okay, or the binary. Let us say we draw something like this. Let me elongate the number of nodes, right? Let me just make it so that we have clarity. Okay, so what we are checking is this is the x, okay, and this is the parent of x, and this is the right subtree of x, and this is basically the left subtree of x. So we are checking if we have marked the left of x as blue, then it is evident that this whole subtree, which evidently contains much more nodes than the whole than the remaining parts, if this counter of the left is greater than counter of the parent, that is the number of nodes falling in this part plus the counter of the number of nodes falling in the right subtree plus the 1 that is for this x value. So if this is happening, this means that we have won the game, right? That is because the left subtree has completely been marked as blue since we start from this node, right? So this condition, if this is met, then we return true. This is the same thing given. If counter of left is greater than 1, that is for the x node, greater than counter of r added with the counter of the parent. So we return true, right? So we return true, and this is exactly the same. Similarly, we pick right of x as blue, and in case counter of left subtree plus counter of parent subtree plus the 1 for the node of x is less than counter of right, in any of these cases, if these are coming out to be true, we win. That is, the number of blue nodes would actually be greater than the number of red nodes. So this is the blue node because we have picked the parent of x as blue, then the counter of the subtree falling under parent would be blue. Similarly, if we pick the left of x as blue, the counter of left would be the subtree, which would be completely covered in blue, and similarly for the right, that would also be blue. And these are all the areas that are marked as red. All the nodes are marked as red. So we want this condition. So that is exactly what has been written here, right? So these are the 3 conditions we check for, and in case these are not true, we return false. That is, we lose. That is, the number of nodes for red are greater than number of nodes that have been covered for blue, and that is the answer. Right, so this is basically the solution, and that's it about the video.